right, everyone. Thank you for coming. My name is Jared Poche, and this session is Every Millisecond Counts, a case study in tuning a frequently used procedure to less than 1 millisecond in duration. A bit about me. I'm a database engineer. I've been working with Channel Advisor for the last 4 years. I started working with SQL Server in 2002. At that point, I was a community college instructor, and I basically taught certification classes. So I did that for a few years, and then I like to say I worked for a little company called Microsoft for a decade or so, and I was working in customer support for them. If you want to contact me after the fact, I've got all my contact details on the bottom left here. I've been blogging about SQL Server for about 1.5 years now. I also have been speaking for other SQL Saturday events, and I was a virtual past speaker last year for the first time. And I'm kind of a performance enthusiast. So this is all about performance and database optimization. And those are the things that I find the most interesting about SQL Server. I love making things go fast. So to set expectations for the session, this is sort of an intermediate to advanced level session. I wanted to do this session because the work that I did at this on this subject last year was really interesting to me because it wasn't sort of standard query tuning work. This wasn't a matter of simply finding the missing index or a table scan that's reading millions of rows. It was, the issues we looked at were a lot smaller and a little more subtle. So the goals for this session is I want you to see kind of the attention to detail we had to put into this to see the opportunities to improve this stored procedure. Hoping you might learn a coding technique or two that you haven't seen or used before. And I want to encourage you to take a holistic view of looking at the problems. Some of the big gains we made in tuning this stored procedure is it required us to think about how the application interacts with SQL Server and how our users interact with our application. So before we get into it, there's a number of topics that come up in the course of this talk, and I wanted to kind of go over them at least in brief first, so we all have the foundation to go forward. So the procedure that I'm tuning here is an upsert procedure. It is trying to insert or update data, and the majority of the time, what it is written to do basically is to go in and try to update several rows in a table, and then it runs an insert statement with a where not exists clause. So basically, if we couldn't update a given record because it wasn't there, doesn't exist, we basically insert that record. I found a really good blog post about upsert procedures and about tuning them and avoiding contention that was written by Aaron Bertrand late last year. This was after I had done this work, but I thought it was interesting that there's a lot of similarity. So I actually do link to that blog post if you're more interested in upsert procedures and how to write them. He's got an entire blog post that's very good that covers several topics and some suggestions for that. We use table variables a lot. And so table variables come up multiple times throughout this. And table variables are a lot like temp tables. They get stored in tempdb. You can define what columns are in them. You can insert rows in them. You can create indexes on table variables. But they do get maligned by one fact. They do not have statistics. So even though they have indexes, they don't have statistics. And SQL Server will then assume that a table variable, it kind of always assumes that they have one row, which may or may not be accurate and can lead to execution plans being less than optimal when you're using table variables because SQL Server is guessing how many rows are in a table variable. But we use them very heavily, so that is a subject is going to come up. Specifically, I use table valued parameters a lot. So you can take a table variable and use it as a parameter for a stored procedure. So instead of passing in, say, one set of parameters for a stored procedure to have it insert one row of data, you can basically pass in an entire table variable with multiple rows of data already in it, and then have SQL Server use that however you want. In the environment I work in, this is really advantageous because imagine if you need to make 50 individual calls to your database to insert 50 rows versus creating a table variable and making one call to one stored procedure to insert the same 50 rows. When you have the more connections, you have more round trips between the application and the database. You also have the potential that all those 50 threads are going to be blocking each other constantly and creating a lot more contention. When you're using a TVP, those kind of operations tend to be more efficient. And also table variables can be memory optimized. So We use memory optimized table variables and memory optimized TVPs very often, and it cuts down on the contention you would otherwise get in TempDB from having an awful lot of objects in TempDB. So table variables are a big topic, and I use them a lot throughout this. Table spool operators. Table spool operators come up as well, and what table spool operators do is they basically, inside a larger execution plan, you might have an operation that creates a table spool. And we're basically taking that internal result set we've created at a specific point, and SQL Server saves off a copy of that so that it can refer to that information later. It might need to take that internal result set and join it several more times throughout its query process. So when you have a table spool operator, you basically have one that's writing the data off, and then you may have multiple operators that are then reading that data later. It's a thing to be aware of table spool operators. It does tend to suggest that you have a reasonably complex process going on, and the table spools themselves are quite a bit of extra work sometimes. Indexed views. So one of the things that we look at is an indexed view at one point, and of course views are relatively straightforward. They're kind of logical constructs, queries that are already defined against a table or a set of tables. You can create indexes on these views. Now, the advantage of that is the data is already kind of structured for the view in a separate place, and so you can run the query against the views potentially faster. The disadvantage is that they have to be updated just like any other index in a table, and it seems like it's another layer of overhead on top of the operation of the underlying table. There was a funny thread I saw, I think late last year. Brent Ozo was making some comment on Twitter about indexed views, and somebody replied to him that indexed views are a separate physical table populated by a trigger. And then he said, "Fight me," in all caps. And I found that very amusing and a fairly good description of the thing. One last thing is the Halloween problem. So the Halloween problem comes up in this presentation later on, and what the Halloween problem is a problem where SQL Server or other database management systems, it's possible if you're changing a row, that a given row might move where it is in the index as a result of your operation, and your query might continue to operate on a row by row fashion and then operate on the same row a second time. That's the Halloween problem. There's actually a Wikipedia page for the Halloween problem if you want to go look up that later, and I'll have some other links about that too. I just wanted to introduce these ideas because all these things are going to come up as I talk about the things I worked on in this case. So this is a case study about a stored procedure that I worked on during my 9 to 5 working with Channel Advisor. So Channel Advisor does e-commerce, and among many things, we do inventory management and updating management for our customers. So in terms of inventory management, we'll track all kinds of details about items they're selling, you know, their dimensions, the title for the item, the prices for it, the UPC code, all those things. This stored procedure is allowing us to update the quantity for those given items. We're updating multiple rows for one item based on a TVP that is input for this procedure. So in the underlying table, we're tracking quantity for a given item, but a given item might have multiple rows because it might have quantity present in multiple different distribution centers. So one item, we can have multiple rows for them to update. The updates are being driven by customer activity. Customers are basically uploading files or working through the API and uploading details to us throughout the day. Frequently, they may have a scheduled file that they upload to us, and you know some of the data might be redundant.
I bought 2 bread. Yeah, which out of that bread?
Hello. Sorry.
I'm going to try to find who it is and mute.
Okay. Sorry. Thank you. So the updates are being driven by our customers. The stored procedure that I was working on, had an average duration of 3.1 milliseconds when I started working on this. And you might ask, why on earth would you bother tuning something that runs that fast? That's because we were running this stored procedure when I started working on this 285 million times a day. Now that's across dozens of servers and hundreds of databases all running the same schema and the same code. But as should be obvious, any improvement we can make on this stored procedure would be multiplied many times. So it could result in a large gain. My original goal was to see if we could just reduce the runtime of this stored procedure by 1 millisecond. And I figured that would be a huge result, and we actually far went beyond that. I'm using Query Store, and I use it on a daily basis, and that's giving me all the times that I'll refer to in this, such as saying this stored procedure takes 3.1 milliseconds. I got those details from Query Store. So the procedure outline, and forgive me, but this is work that I do during my day job. So I'm going to talk about this. I have to use, I'll show you the anonymized execution plan, but I can't show you the actual code. So the stored procedure really does 4 things. It populates a few variables early on. That statement's not really consequential. It checks for item listings. So if you have, say, 20 of a given item that you want to sell online, imagine if you've already put 5 of them on some marketplace. Let's say you've got them posted for sale on eBay. Well, you really don't have 20 available anymore because 5 of them are kind of already spoken for. One of the queries in this procedure checks to look for existing listings of items so we can subtract that number out later if we need to. This is also not a huge part of the work we're doing in this procedure. We perform an update to the underlying table. This is about 80% of the runtime of the procedure when I started working on this. So it was obvious looking at this even briefly that we're going to have to handle that update and see what we can do to make improvements there. And then we do, since this is an upsert procedure, if one of the rows we tried to update doesn't exist, so if the quantity for that item on a given distribution center does not already exist, then we're going to insert a row. And I realized as I started looking through this that the insert is going to cause us to run a trigger that does a change on another table. So that's our starting off point. All right, so here's a snippet of the execution plan, and actually I think I will switch over to I'm going to switch over to Management Studio for a couple of things. I mentioned table variables a couple of times in here, so I'm going to set up a little bit. I'm working with the AdventureWorks 2014 database. I've already restored this database from backup. And what I'm going to do is I'm going to set up things so that we can use in an example later on. I will be using memory optimized table variables. So here's a script. All I'm doing here is creating a new file group that contains memory optimized data. And this not exist check here will create it if, of course, the file group doesn't already exist. And we're going to create one file in that file group. So that is done. And one more thing, this is a table variable. I'm going to create a type. Here's the name of that type. It is a table. We've got 3 columns for it. I'm creating an index on it, and I'm specifying that this table type is going to be memory optimized. And I'm creating a second one below with a few more columns. So let me create those real quick. Well, or real slowly, but yes. Now, the next thing I was going to do is actually start looking at the execution plan with you. And I've got a snippet of it here, but we can actually look at the entire thing in Management Studio. So here is my update statement. Now, looking at this at first, this is very complicated. There's a lot of things going on here. There's an awful lot of operators. But at first, it really wasn't obvious what the problem was. It wasn't really obvious if there was anything I could do here to substantially improve things. And I said earlier on that there were no, table scans or anything like that. And if you're sharp-eyed, you might say, well, that's not exactly true. We've got an index scan right here. And again, forgive me for the anonymized nature of this. That index scan is actually on one of our memory optimized table variables. So we're reading one row out of an object that's already in physical RAM. So I'm not too concerned about that one. We're also reading a table variable here and here. What else do we have going on here? We're actually hitting the physical table that we're updating 3 times. We've got a non-clustered seek there. We have a second non-clustered seek here, and we have a key lookup. I did kind of key on the fact that we're hitting the table 3 times for this, and I always like to pick on key lookups when I see them. But additionally, I saw we've got some table spool operators here, but I'm not too worried about the ones here. Their cost is relatively low, and we don't have many rows affected here. You might also notice from all of these operators here, there's multiple joins and multiple scalar operations, but there's very few rows in any of these operations, 1 of 1, 1 of 2, 0 of 1. So the estimates are all very small for this. So what's actually the problem? What can we actually do about this? The first thing that I keyed on as a real problem was
Jared?
Yes.
Sorry for interrupting you, but before I forget, there is a question. Not sure about the architecture, so just asking, but putting a synchronous trigger, presumably instead of on a table being updated at least 285 million times a day, sounds like something to be avoided at all costs, doesn't it?
Yes, it does. I'm not a big fan of triggers in general. There are reasons that we have things on that we do have triggers on some of our tables. It was a good benefit though. We had an additional benefit of one of our optimizations later because of the fact that the table does have triggers on it. I do like to avoid them whenever possible, but sometimes they are necessary. So here's where I started actually finding things that I had more serious questions about. So once we've joined up all of our data, I can see we've got a sort operator, and here we actually update our underlying table. Okay, great. And then I noticed this. I saw, why do we have a table spool operator after we've already updated the table? That's really strange to me. And well, we're reading that table spool here, and okay, we're probably reading the same data here as well. But this middle line was very interesting to me. We've got a table spool, we have a sort operator, we do a clustered index seek, we're looping, we're sorting, and we have another clustered index update. And it took me a minute to figure out what was going on here. I was like, we've already updated the index. That's the green box up at the top. And what I realized is, oh, this is a indexed view. We have an indexed view here. That's what this entire middle branch of this execution plan is about. We're spooling our data from earlier, we're sorting it, we're reading the indexed view, and then we're updating that indexed view later. And it looks relatively expensive here. If you add up the things here, this middle line is like 59% of our cost. Now, cost is always an estimate, and do keep that in mind, but it started looking to me like this, keeping up this view is actually costing us quite a lot. So that is where I got started in analyzing this thing. So I started asking myself, okay, we probably need the view, but do we need the index on the view? And this led to some additional ideas. So first, I'm worried about the view updates and how much that's costing us. Second, I thought about it and I said, okay, how often do you insert a record? Well, you insert it once. And we're going to be updating quantity on items really frequently. So my thought was, well, what percentage of the time do we actually need to do the inserts? Are they unnecessary? And if they're unnecessary, can we skip that effort? Also, this was not something I knew before I started this. Let's say you run an insert statement with a where not exists clause, and it inserts 0 records. You still run the trigger. And that was hilarious to me. I did not realize we would run a trigger on an operation where we actually affected 0 rows, but we will. Third thought that I had is about table variables themselves. Because SQL Server doesn't know how many rows are going to be in a table variable, might we be better off with temp tables? Would the SQL Server be able to come up with better execution plans at that point? So that was something I wanted to test out. And then finally, there was the update statement itself. And like I said, that was the majority of our execution plan. So I wanted to take a look at that and see if we could get rid of the key lookup at least. And I also wanted to try and address the fact that we referenced the table a total of 3 times. Let me go back and do one more thing real quick. One more thing about the execution plan here is the cost of this operator, the clustered index update. I would say in general, if you've got an insert, an update, any DML operation, the most expensive operator tends to be the one that's actually writing data. So if you're doing an update statement, I would expect the clustered index update to be the most expensive operator. Here it's only 22% of the cost. For something that's really well tuned, I'd expect that to be much higher. I'd expect it to be 70 or 80% of the query. And what this tells me in part is there's a lot of things going on here inside our update statement. So that was one more point I wanted to make. So I've got 4 ideas at this point, and we're going to walk through them real quick. So The indexed view itself. So this requires the table spool operator. It's kind of expensive. We're updating the view as part of our update. And like I said, DML operators are much more expensive than just reading our data. Well, so I asked questions and I had to go look at the view and like, why do we have an index on this view? Well, as I mentioned, an item may have multiple rows in this table because it may have quantity in different distribution centers. All the view is doing is really aggregating it. So if the item has 4 rows, the view is going to have one quantity number for us. So, and looking into it, I know that most items don't have many rows. They're only going to have a handful of rows. So maybe it's saving us from reading 4 or 5 rows, and instead we're only reading 1. That doesn't seem like a big difference to me. So I did some research and looked to see if there were any procedures that might be negatively impacted from removing the index. And I didn't really see anything, so we removed it. I didn't really have a great frame of reference for how much that would optimize things, but in this case, it reduced the runtime of the procedure by about 20%. And I say 17 to 25%. This is all from Query Store, but it depends on kind of what day you measured it from. But it was about a 20% reduction. That's honestly really huge. At that point, that's more. I was trying to reduce this procedure by 1 millisecond. Well, that just gave us 6/10 of that. So this was a good start. Second idea, memory optimized table variables. And excuse me for 1 second. So memory optimized table variables, they don't have statistics, and SQL Server is going to have bad estimates. It's always going to assume 1 row. The bad estimate could lead to bad execution plans. Now, temp tables will have statistics, and SQL Server might make better choices based on that. So my thought was, what if we took out the table variables and actually had us joining 2 temp tables? Would that improve our performance? And the answer was no. That was a terrible idea in this case. What this caused for us is we ran into a lot of temp-to-beat contention, and the procedure actually started taking longer. And this may work well in other cases, but in our case, the fact that we're running the stored procedure as many times a day as we are, and the fact that we were using several table variables, so we had to create 3 or 4 temp tables, just creating way too many objects in tempdb and caused huge tempdb contention. So we ended up reverting that change. So I'm a very big fan of using memory optimized table variables. I like how fast they are. And I would say if you want to get a specific behavior out of a given execution plan, if you want the plan to go down a certain path, I think you'd be better off, say, giving SQL Server a hint or fixing an execution plan in Query Store. So this was an example of something that did not work. Next, I mentioned the idea of having unnecessary inserts. So the stored procedure, we try to update a number of rows. Let's say the TVP for our procedure has 3 rows in it. So we try to go update those 3 rows, and afterwards we will try to insert any of those rows that don't exist. And the idea is we're only going to insert a record once, but we're going to update it many, many, many times. How often do we call this procedure and the insert ends up inserting 0 rows? Well, let's skip that effort if we can. And the logic here was actually really simple. So if our TVP has 3 rows and our update statement updates 3 rows, we shouldn't have anything to insert. So here the logic was really simple. We just checked the row count of our TVP initially, and then we checked the row count from our update operator. And if they're the same, then we completely skip our insert statement. That dropped us from running that insert statement at this point 350 million times a day, down to 6 million. Now, it didn't make a huge difference in terms of our runtime. The average duration dropped from 1.95 milliseconds to 1.91. Still, that comes out to 14,000 seconds a day. And it also meant the trigger that is executing as a result of this insert statement also dropped significantly from, I think, about the same number of executions. So from 350 million to 6 million. And I think it actually saved us more time on the trigger than it saved us on this procedure. But still, this was a small win, but I definitely took this as a win. So those out of the way, we're back to looking at the update statement. And our update is relatively complicated, as you can see here. So, and we actually have two update statements in the procedure, and depending on the parameters that are passed in, we run statement 1 or statement 2, but otherwise, they're pretty similar in most respects. So I looked at several things in it, and I saw we actually had a common table expression at the beginning of our query that was doing an aggregation step that we didn't really need. We had a second reference to the base table in another common table expression. And actually, let me step out of this for a moment back over into Management Studio, and I'll show you kind of an example that's close to what we were doing in our update statement. So this is in AdventureWorks. And here's an example of what I was seeing. So in this query against the sales order detail table, I've got a common table expression where we're returning some data from the underlying table. We're joining between our TVP and the sales order detail table. And we've got case statements that are returning data from the underlying tables. Great. Then we use that common table expression in our update statement. And we join from the CTE to the underlying table and another table. And we have another round of case logic that's actually deciding what values we set in the sales order detail table. So this is what my update statement kind of looked like to start off with. And part of what I realized is, well, we're referencing the sales order detail table twice because we've got this case logic that we've broken up between the two of them. And I looked at it and I decided, you know what, I looked at it and I basically sorted out all the possibilities for the case logic, and I just rewrote them. So I had one set of case logic, and I got rid of the CTE altogether. Now, what this meant is I went from having two references to the table in my statement to from having two references of the table to only having one. Now, at that point, I still had a key lookup. And like I said, I am not a fan of key lookups, especially with larger result sets. They can be really, really detrimental to your performance. So I unified the case logic and got rid of the common table expression. So I started looking at the key lookup, and actually, let me see if I still have the execution plan handy. I do not. Hold on. And what I was going to point out is when you look at your key lookup operator, apologies. If I mouse over this first, that'll be a lot better. When you mouse over it, you can see what's in your output list. These are the things that we're actually having to perform the key lookup for. We need to get column 1 and column 7 in our result set so that we can complete this query. That's why we're using the key lookup. So I started with that, and I was trying to figure out how we could eliminate the key lookup. And I realized something weird. Our clustered index for the quantity table has the account ID, the item ID, and the distribution center ID. But the non-clustered index that we're using starts off with the account ID, the item ID, and the distribution center ID. They're the same, at least the first 3 columns are. And it seemed weird to me that the SQL Server had chosen to use the non-clustered index if it was going to then have to do a key lookup anyway. So I put a hint in this statement to have it use the clustered primary key to start with. So instead of hitting the non-clustered index and then doing a key lookup, we just do a seek against the clustered index. All these optimizations went out together, and it reduced the runtime of the procedure by 28%, saved us about another half a millisecond or 189,000 seconds a day. So this was huge. And at this point, we had done a really good job. We had achieved what I had set out to do and reduced this procedure by a millisecond. And look at this execution plan and think about what I was showing you earlier for the update statement. We hit the underlying table, we scan a table variable, we seek on the other table variable, we aggregate things together, and now look at that clustered index update. Now it's 73% of the cost instead of being 22% of the cost originally. That operation didn't get any more expensive. We just trimmed that much of this statement away. And I think a really big part was simplifying the code of the query itself and simplifying the logic of it, but also getting rid of that index on our indexed view. So at this point, we've gone from 3.1 milliseconds down to 1.4. But we had an additional idea. So in the same way that our inserts were frequently unnecessary, we kind of felt strongly that our updates were as well. Customers upload information to us about their inventory all the time, and we know that data is frequently redundant. Customers will just upload like kind of their entire library of items to us that they have for sale, and those details don't frequently change. The application is cached to deal with that and to not send changes down to the database. But we can't really do that for quantity because we need quantity to be correct, and we need it to go through very quickly. So we kind of felt like people are uploading the same quantity information for items over and over. Set the quantity for this item to 5. Set it to 5. Set it to 5. Maybe they're uploading the data every 5 minutes, or maybe they're uploading it every hour. But we think a lot of these updates are redundant. Well, could we skip running the update statement if all of the data they're passing in on this procedure call is redundant? So the idea would be to limit the updates to when the quantity actually changes. So my first thought was this: let's add a where clause and say where the old quantity is not equal to the new quantity. So we'll go into the update statement, but we'll filter out the rows that aren't actually making changes. How about that? And this was a terrible idea. In our case, this is where we ran into something called the Halloween problem. And I think I had read about this before, but I had never seen it in the field, so to speak. And kudos to Kevin Fiesel, who is one of the gentlemen I work with. He's actually presenting, I think, in one of the rooms for the next round. He looked at the problem with me and thought that this was the Halloween problem. That did turn out to be the case. So the Halloween problem can affect any DML operation: an insert, a delete, an update, or a merge statement. There's a link here to a series of blogs from Paul White, so SQL Kiwi, if you're familiar with him. He did something like a doctoral dissertation on the Halloween problem. He had like 4 really detailed blog posts. I have a blog post on it too, but I was not trying to invent the wheel here. I just wanted to cover the basics of what this is doing. But the gist of the Halloween problem is this: if you are querying for a thing, if you've got a field in your where clause, but you're also trying to change that field, you could run into something called the Halloween problem, which is where it's possible for SQL Server to say update a given row a second time. This only happens when it's processing things in row by row fashion. But and this is actually a really good example of the Halloween problem. But SQL Server knows the Halloween problem exists. This has been around since the late 1970s. The Halloween problem was actually discovered in a database, in an IBM database system at that time, if you go look up the Wikipedia page for it. SQL Server knows this problem exists, and it prevents the Halloween problem, typically by changing your execution plan and putting in blocking operators. So it stops it from running in a row by row fashion so that you're not reading a row, changing it, and then continuing to read more rows and maybe finding that same row a second time. So inserting these blocking operators prevents the problem, but it's not great for performance. So we had to get around that. And my idea was this: what the blocking operator SQL Server injects is trying to do is it's trying to separate the reading of your data from the writing of your data inside this update statement. And I thought, well, why don't I take it to the next step? Why don't I have 2 queries? Why don't I split the operation? Why don't I query all the data that I need from the TVP and the underlying table and put that into not a temp table? That would be terrible. Why don't we put that into a memory optimized table variable? And that table variable will have the old quantity and the new quantity for this item in all the distribution centers. Then we can check the results in the table variable. If there's no changes according to the table variable, we skip the update statement. We don't even run the update statement. We go right around it the same way we've been going around our insert statements. We also had to change our insert logic here. So previously the insert logic was based on row counts, but now we might not be updating rows at all. So we changed it to also be based on the logic in the memory optimized table variables. So we're doing a left join from the TVP to the underlying table so we can see when rows don't exist, but they should. Part of my concern with this approach, though, was I went from having an update statement to having an update statement that we might run and a query that's populating the table variable and then reading the data from the table variable. And I wasn't quite sure how much overhead that was going to add to us. But I was pleasantly surprised to see just how fast this was. So the query to insert into the table variable took 90 to 100 microseconds. Checking the results, so running the query to say if not exist or if exists, data where we're changing the quantity, that query took 10 to 20 microseconds. Adding the new logic allowed us to skip the update statement 96% of the time, at which point this stored procedure was taking 320 microseconds on average. This is almost a 90% reduction from what we started off at when we were really looking to just drop it by a third. So this was a huge optimization, and I was very pleased with myself afterwards. So before we've still got plenty of time, so I'm going to come back to these in a minute. I've got some more examples I can show you over here. So in Management Studio, I've created our table types. I've set up the memory optimized file group. And now what I'm going to do is I'm going to show you the before and after. Like I said, I can't show you the actual code, but I can show you something kind of similar. Oh, let me also turn on Query Store. All the numbers I've been talking about, and especially getting things down to the microseconds level, that's because I'm using Query Store. So let's turn on Query Store inside this database. That is done. Now, here's a stored procedure that's based on the AdventureWorks database. That's again based around the sales order detail table. This is kind of like what my production procedure was doing. So I've got a procedure that's taking in a TVP of one of the memory optimized types we created earlier. I'm doing a little throwaway query here to see the status of the order in the sales order header table. Fine. Now, depending on the update type that is passed in, we'll either do a relative update or we'll do an absolute update. This is similar to the way my procedure had two different update statements that were similar but not quite the same. So if it's a relative update, we'll take whatever is in the TVP, we'll join to the sales order detail table, and we'll update the quantity and the price based on what's in the TVP. And we're joining based on the product ID in the TVP, joining that to the underlying table, and we're passing in a sales order ID with the stored procedure as well. So we either update the rows that are in the TVP, or if you tell it to do an absolute update, it'll update things that are in the TVP. And if there's a row in the underlying table that's not in the TVP, it'll actually delete that out of the underlying table. So it'll do a delete statement. And also, if what you have in the TVP is not in the underlying table, we'll try to insert that later. So this is an upsert procedure as well. So let me run that real quick. Okay, so now that procedure exists. Here's a modified version. So this is the same procedure, but written with the additional logic to put information inside our table variables and decide, do we need to insert, update, or delete? So what I'm doing here is, for my incremental change, I'm querying from the TVP to the sales order detail table and inserting that into my second table type that I created earlier. And we're putting in there the quantity from the TVP and the quantity from the underlying table, the unit price from the TVP and the unit price from the table. Now, if any of those things changed, if either of those things changed, if we change the price or we change the quantity, then we'll actually run our update statement. Otherwise, skip it. Was there a question? Okay.
No, I think it was your echo. No.
Okay. In the second example, if we were doing, say, an absolute change, we again query logic into our table variable. We actually do a full join instead of a left join here. And if there's no changes, we skip the update. If there are changes, we run the update. If there's anything in our table variable where the new values are null, well, the new values are the values that come from the TVP. So if the record wasn't in the TVP, but it's in the underlying table, then we want to delete that, in which case we run the delete. But if there's nothing where these values are null, then there's no records for us to delete, and we skip the operation entirely. And down here, we check the DC changes again, and if the current values are null, then that means it's not in the table currently. So if there's anything where the current values are null, but they are in the TVP, then we of course need to insert them. So let me run that. Okay, now that version of the procedure exists. So here's what we're going to do. And what are you? Oh, that was my example from earlier. So what this script is going to do for me is it's going to retrieve the details for one specific sales order ID, stuff that into a table variable, and now we're going to run a transaction and run my original stored procedure, doing changes that are redundant, setting everything back to the current values in the table, and then reading out what's in the TVP afterwards. But then we roll back the transaction so that we can do the same operation with the new procedure, and again rolling it back. So let me run that once. Okay, here's all of our details, and all of this is up on GitHub, all of my slides as well as my scripts. So if you want to go through this yourself, you certainly can. This is a query against query store. We turned on query store earlier in this database so that we could see how quickly this would perform. So let's take a look at the details. Now, this is the old version of the stored procedure, SP detail. And you can see in this, now the times, the average duration and CPU times, all of these are in microseconds in query store here. So you can see we've got the delete statement that was relatively quick, the select, the insert. That update statement took 300,000 microseconds. So it took 319 milliseconds. Okay, that's fine. Now the new version of the stored procedure that's using the additional table variables, if you look in the query text here, you can see there's no delete statement. And I don't see the insert and I don't see the update because we didn't actually run any of those statements. We didn't execute them. So I don't have any performance details for those at all. But what you can see here is our multiple if exists statements trying to determine whether we need to run any of those. The longest running statement here is actually the statement to populate our table variable. So the original join between our TVP and our physical table. So we take that information, we store it in a new TVP. That took 7 milliseconds. Now, from my example from what Channel Advisor runs, that was taking 100 milliseconds to populate the table variable. So you might be asking, what's the difference? Well, I'm running this on my home computer. My computer is, running presentation software. I mainly use it to play games on Steam. I've got all kind of the normal things that you run on a home machine, which would be different than you have on a production system. So I'll put a big, your mileage may vary depending on the server. But even here, you can see that using the memory optimized table is a lot faster than doing the unnecessary operation against a physical table. So here we're talking about a few milliseconds versus hundreds of milliseconds with the previous style of the stored procedure.
I'm up here, hold on.
Hello?
No worries, I took care of it.
I'm sorry, what was that?
Go ahead, I muted the person.
Okay. All right. So that is everything I wanted to cover. We haven't really had much questions in this session. If anybody has questions, I am all for taking them. Here's a few references about things that I mentioned as I was talking through. So Paul White had a really good series of blog posts about the Halloween problem. And so I linked to that here. Earlier on, I mentioned that Aaron Bertrand had a really good blog post from late last year about upsert coding patterns. So if you're interested in how to write those things, he specifically talks about the kind of contention you'll have in upserts, and in a couple of cases he had some hints that he suggested, I think table hints or index hints. No, it was locking hints actually, that would allow those operations to run more efficiently. I have blogs of my own about the Halloween problem, about blocking operators. That was one of the first things I blogged about, and this topic and the optimization of this stored procedure. So if you want to take a look at those, please feel free. And if you don't use table variables, you might find it interesting just to read through TVPs and what you can do with them. And if you have any questions or want to follow up with me later.
So the question is, does switching on query store cost performance impact on production system? So basically the overhead.
Can it? Yes, and there are other people who could speak more about that. I know that one of the bigger problems some of my coworkers, and I'm not a database administrator, so I don't actually handle that part of it. But I know that one of the bigger things that they encountered was some issues with the cleanup operations inside Query Store. So they've actually they actually wrote some code of their own to clean up old data within Query Store that gave them a positive benefit. But yeah, there is something to how you configure Query Store. There is an overhead. It should not be considerable under most cases, but it depends on how you configure it and how long you want to retain information inside the system. But at the other side of that is you get such a wealth of information. Being able to go back and refer to execution plans, and okay, they'll be basically you won't have all of the runtime statistics of them, but being able to see variations in how a stored procedure executes over time, being able to see different execution plans for it, being able to see specifically which statement inside a stored procedure is the one that's taking up all your time. It provides a wealth of information for it, and I honestly, I could troubleshoot SQL Server without Query Store, but I don't want to.
So that doesn't look like a question, but rather a comment. I'm looking at the logical reads with actual time, great optimization techniques. Next one, what is your GitHub site?
Oh, my GitHub site is, actually, I don't have that in my slide deck. I do have.
You can paste it into the chat if you can.
I will. Okay, I know that I tweeted about it last week, so you can check my Twitter and it'll be there. I will actually put out a tweet as well on my at sqljared. I will once we're done here, I'll tweet out that location again for you. I don't have it at hand.
No
I have
problem.
to go looking for it.
I see somebody just said that they know sqljared.com, so they know your site, and looks like they're looking forward for the URLs for those references there as well.
Okay. So yeah, I did post it on my blog site, at least a brief post there as well.
So GitHub sqljared, okay.
Yeah, that's easy enough to remember.
Looks like somebody knows your GitHub.
Well, I'm glad. I'm glad to know that people are using it. That feels great. I actually created that. I presented the same information for the Southwest Data Saturday, so I posted it then.
This is actually quite helpful because this allows you to control the content. You, the original owner of that content, and instead of us trying to host it somewhere else and then it gets not updated, this way, one link, people can download, do whatever they want with it.
Right. I entirely follow. It's been sort of inconsistent in other events that I've gone to previously. I like the idea of actually having this up on GitHub.
Yeah, because this way you're actually not bound by the event. This way you're just sharing it with the community without the event.
Right, and I want people to be able to see the all the links and stuff, so they can find all the resources if they're interested in any of them. I suppose I can stop sharing at this point.
Oh, looks like your GitHub doesn't have a public repo.
It doesn't have a public repo. Okay, I will work on that then.
Okay. Okay, so since we have all the emails of attendees, again, with the recording, we'll share much more stuff. So again, we can fix it, I guess, after the event.
Yes, I will make sure that I get that sorted out.
Okay, we have 7 minutes. Well, this was a very interesting session, especially with Query Store.
I really didn't use Query Store before I started at my current employer, but like I said, I really, I'm a huge fan of Query Store now because of the amount of information it puts at your fingertips.
Okay, so one more comment. Thank you for great presentation, and looks like we will have one more question. Okay.
So you set up DB altered on memory optimized on.
This is probably a hint.
Yes, well, I mean, early on, I did the scripts that I ran to do the initial setup early on. I created the memory optimized file group so that we could create the memory optimized types later. So yes, that was a part of the process, and that's in the scripts, and the scripts are all in the GitHub. So I'll make sure that the GitHub is available for people to get to. And if you want to take a look at, say, how we turned on Query Store, or something small like that, or something like how do you set up a memory optimized file group, that's in the files.
Okay, good. Now keep talking, keep the camera on. I'll take the screen share back, and I'll put the QR code for your feedback.
All right.